Greetings and welcome to the Chemistry 223 lecture for Chapter 15, which I call the Precipitation Reactions chapter. We're going to look a lot more in this chapter as to what exactly constitutes precipitation of a solid, or making a solid appear when none appeared. And as we've seen, some solids appear really quickly, other solids take a little bit longer. It takes more chemicals to make a solid appear, and some of them arguably never make any at all, or at least not for a long, long time. We're going to use the ideas of equilibrium in this chapter to help explain what exactly solubility and precipitation is all about. And it'll be really interesting, I think, for you to look back in your Chem 221 notes, if you took Chem 221 at Mount Hood, that is, and look at our solubility guide that we looked back there. And you'll see why maybe we made some of the decisions that were on there, but we'll also see now that was a very shallow way of looking at precipitation. And we're going to look at a much better way in this section. So let's look at this video and then we'll get into the lecture.
When a solution containing iodide ions is added to one containing lead 2+ ions, a precipitate of lead iodide forms. This precipitation reaction occurs because lead iodide is an insoluble ionic compound. Hydrated ions release water molecules and form the ionically bonded solid.
So this little video shows something which you maybe didn't think about that much, but it shows how lead to iodide, a solid, appears. And in this, they basically added some lead ions to some iodide ions. And normally when an ion is in water, it dissolves, it's hydrated. And this was the ion dipole force we saw back in Chem 222. But anyway, when the lead and the iodides come together, there's a desire for them to make a solid, all right? And when that happens, in this case, two iodides react with one lead 2+ to make PbI2, which is that cool kind of yellow compound. But it's kind of interesting because initially everything had water around it, and the waters were essentially excluded then when the PbI2 came around. And this is kind of the basis of what we're going to be looking in this chapter, like how to predict when the solid begins to form. Maybe there's some threshold needed to actually make the precipitation occur. The answer is yes to that, by the way. Oh, spoiler alert. Anyway, we'll see lots of things that affect solubility in this chapter. In Chem 221, if you took it at Mount Hood, or if you didn't take Chem 221, no worried, we use this table right here for solubility. And if you haven't seen this before, if you haven't seen it for a while, in the upper left-hand side are a bunch of ions, which when they form with a compound, they are always water soluble. So example, you can see up there that everything basically was sodium, potassium, ammonium, as well as nitrate, chlorate, perchlorate, and acetate. All of those are soluble all the time. So you could make a brand new compound. It would be sodium blah, 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 and I don't know what blah, blah, blah is. I've never heard of it before. It doesn't matter. Because it's got a sodium, I would say it's water soluble. It could also be blah, 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 nitrate, and again, I have no idea what that first part was, but the nitrate tunes me in as a chemist to say, hey, I bet that's water soluble. Now, remember that most of the ions of chloride, bromide, and iodide are aqueous as well, but there are three important exceptions, and those are silver, mercury, and lead 2+. So, for example, in the video we just watched, that was PbI2 forming. Most of the time, iodide is soluble, all right, but when it's with lead or silver or that mercury ion, then you're going to have an insoluble compound form. In Chem 221, we also talked about like how barium sulfate was a fairly common exception to the sulfate rule. We also talked about how most of the negative ions down here, most of those are insoluble, which means they would form a solid right away unless they are with ammonium. The alkali metals, remember, are everything in group 1A, so that would be potassium, lithium, sodium, etc., etc. So just to make sure we're all on the same page, I have here three examples on the right, and you can tell which is soluble and insoluble from where they are on the chart. So barium nitrate. Okay, nitrate is one of the ones that's always aqueous, so barium nitrate absolutely would be soluble. No exceptions to the nitrate, notice that too. Now, barium chloride, all right? Chloride is right there. Chloride is usually AQ unless it's with silver, mercury, or lead. Barium is certainly not silver, mercury, or lead, so we would say that BaCl2 in water is soluble. It's aqueous. It dissolves. Finally, though, barium sulfate. Now, most sulfates are aqueous, soluble, all right? Barium is one of the exceptions. So barium with sulfate, we would say it makes an insoluble compound. And really, we should write this then as BaSO4 solid. If something is insoluble, that means you'll put a little S next to it. It's insoluble, all right? And if something is soluble, then you'd put an AQ next to it. So the first two were absolutely correct. Those were soluble, and you should write AQ. But this last one, it should be BaSO4 solid. Sorry, my S's are pretty bad here as I write on this. Barium sulfate is insoluble. It does not dissolve well in water. This is a quick overview of the rules we looked at from Chem 221. And this list does have utility even now. There will still be uses for it. But now what we're going to do is look a little bit closer as to why some of these, like barium sulfate, are insoluble, and also why some of them, like barium chloride and barium nitrate, are soluble. Like what's making it, and can we predict when it's going to precipitate, etc., etc. So let's consider taking sodium chloride and dissolving it in water. Now, table salt is what sodium chloride is, all right? And I used to, as a joke, put sodium chloride in my friends' like Diet Cokes, which was really dumb and immature, but, it was, just a few years ago. No, seriously, it was a while ago. Anyway, it was kind of funny because when sodium chloride, it dissolves so well in water, or Diet Coke for that matter, that you can't see it, all right? Nothing happens. So sodium chloride, you can dissolve a lot of it in water. But the question is, can you dissolve all of it in water? If we're going to write an equilibrium, let's write it like this, where the precipitated version or the solid version is the reactant, and the ions that go into it are the products. So for sodium chloride, we would say NaCl solid on the reactant side, and then Na plus and Cl minus, the dissolved ions, aqueous, on the product side. And again, this is an equilibrium.
When a small amount of sodium chloride is added to 100 grams of water, it dissolves. If we add more and more salt, eventually no more can dissolve in this amount of water. The quantity of salt dissolved in this solution, about 35 grams at room temperature, is a measure of sodium chloride's solubility in water.
So in this example, it took a lot of table salt, sodium chloride, to not dissolve, all right? But that 35 gram number is important. That 35 grams represents, if you will, the capacity of that amount of water to dissolve sodium chloride, turn it into sodium ions and chloride ions. Once you get past 35 grams per 100 or so milliliters there, then the water no longer has the capacity to dissolve the sodium chloride. And that's when you begin to see the precipitate on the bottom right there. So we refer in science as the solubility as like literally a threshold, all right? It can be measured in grams or moles or whatever, but it represents the amount of a solute to dissolve in a given amount of solvent, all right? And when you get over the solubility, over that threshold, that's when solid begins to appear. But if you're under that threshold, and as long as you keep stirring things up, then the solid continues to dissolve. And all substances have this threshold, this solubility in water, and that's what we're going to talk about in this section. When we talk about solubility, it's very important to use the same form of solubility. So we'll always have the solid as the reactant and the ions that go into it as the products. Remember that as we go through this section. The silver, lead 2+, and mercury 2,2+ ions, those three ions together are called the silver group, and they have very similar reactivity. That's why they're called it. All three of those, if they react with chloride, bromide, or iodide, they do make insoluble compounds. So with chloride, you would make silver chloride, lead 2 chloride, and Hg2Cl2. The Hg2 2+ ion is a diatomic cation ion. It's two cations that are connected together with an overall +2 charge. It's a lot of interesting science behind the Hg22 plus ion. We're not going to talk too much about it here, but just realize it is one of the different things. Anyway, all of these ions, when added to a chloride source, they are said to be insoluble. They make solid precipitates relatively readily. They happen pretty fast. It doesn't take too much of any of these things to make the ions, and this can be useful if you want to separate the silver group from other ions.
When moderately concentrated solutions containing silver ions and chloride ions are mixed, the resulting solution is supersaturated with silver chloride. A precipitation reaction occurs until the system reaches equilibrium. In this model, the red and white molecules are water. Chloride and silver ions, gray and green respectively, are in solution. When they encounter each other, they bond and bind with other silver chloride molecules that have precipitated from solution to form the solid.
When you remember how many molecules are running around in any sample that we use, i.e. 10 to the 23rd water molecules or something like that, it's amazing that silver and chloride ions honestly can find each other, but they do, all right? There's like a natural inclination of them to actually want to bond together, which is pretty interesting. So when silver and chloride come together, like all ionic compounds, they make a three-dimensional lattice network. We talked about these a little bit in Chem 222, where you have alternating silver chloride, silver chloride, silver chlorides. Very, very strong. The ionic bonds between them, pretty tough to break. All of the salts, all of the ionic compounds that form in this experiment are said to be insoluble, all right, which means they make solids. But because there are 10 to the 23rd or so at one time, honestly, not all of them are forming solids. Some of them are staying as ions. And this brings up the idea of, again, of equilibrium. In reality, all right, we don't have all of the silver and chloride ions making insoluble silver chloride solid, all right? Some of them remain as little tiny individual ions. And this is the joy, if you will, of equilibrium. We can use equilibrium to describe how little or lot of the ions you need, and you can also think about it then as how much you need to make the precipitation occur, i.e. what is the solubility of silver chloride, how much of it does dissolve per liter of solution, or how many grams can you get to dissolve, etc., etc. If the equilibrium has been established, then no more silver chloride can be able to dissolve, and you'll just start making more and more solid. And at this point, another term that's used sometimes is that the silver chloride solution has become saturated. And saturated just means that you are making solid, and it's going to be very difficult to go back unless you start doing other things. Saturation just means that the liquid literally has no more capacity to dissolve the ions. They start finding each other, all right? And when that happens, you see precipitates and stuff. In the video we showed earlier with silver chloride, it said that the silver chloride was supersaturated. That means that you have solid forming, but maybe if you'd stir it up a little bit, it would go away. Supersaturation is like a quick knee-jerk reaction, I guess, to when ions come together. In reality and stuff, they take a little bit longer. You have to let them stir and wait and stuff like that to see. Don't be too worried about that. Saturated just is another term for having a solid form. Unsaturated means that you are below that threshold, and really then you won't have any precipitate form. People have studied the silver chloride reaction in a lot of detail, and they find that the solution is saturated, i.e. silver chloride solid begins to form when the silver ion concentration is 1.67 times 10 to the minus 5 moles per liter. That's a pretty small concentration. It doesn't take a lot of silver ion to make this happen. The solubility of silver chloride then is also equal to this number, because if you go to 1.68 times 10 to the minus 5th, just a little bit more, that's when you're going to start making a solid. If you're at 1.66 times 10 to the minus 5, just a little bit under, you won't see a solid. So the solubility, again, is literally a threshold as to when you see solid and when you don't. So if you have a silver ion concentration that's just a little bit less than 1.67 times 10 to the minus 5 moles per liter, no solid. But if you get just a tiny bit more than that number, that's when you will see a solid. Chloride should be the same as the silver ion. When they measured the silver ion above, it was in a silver chloride solution, and silver chloride breaks down evenly to silver and chloride. The stoichiometry of silver ions to chloride ions is 1 to 1. One silver ion for every one chloride. So that means chloride and silver ions both are at 1.67 times 10 to the minus 5 moles per liter in this example. We'll talk about when those numbers maybe aren't equal in a later section. This is an equilibrium. Silver chloride is a solid, makes silver ions and chloride ions as products. And remember, in this chapter, you always want to do that. Solids on the left, ions on the right. The solution concentrations of both silver and chloride ions, 1.67 times 10 to the minus 5. Well, we can define the equilibrium constant value using these numbers because, like all Ks, products over reactants don't include solids and liquids, so no silver chloride solid. Silver ions and chloride ions count. They're both 1.67 times 10 to the minus 5, so you take that number and square it or multiply it by itself. 2.79 times 10 to the minus 10th. And if you think about this equilibrium constant, it's a number much less than 1. That means very reactant favored. That tells us as scientists, silver chloride as a solid wants to form. All right, it's going to be easy to form because that K is so small. The silver chloride really wants to form. And I would argue that PbCl2 and Hg2Cl2 both have really small Kcs as well. The numbers will be small because the solids form so easily. So notice here that the solubility is this number, 1.67 times 10 to the minus 5. The K value, the equilibrium constant, 2.79 times 10 to the minus 10th. Solubility is different than an equilibrium constant, and we'll come back to that in a little bit. This Kc that we calculated, 2.79 times 10 to the minus 10th, it actually has a special name. It's called a KSP, a solubility product constant. It's the product of solubilities. I guess that's where it comes from. Anyway, I don't know. But anyway, KSP is another kind of equilibrium constant. And KSP is used for figuring out when solids form and when solids don't form. KSPs are just as handy, arguably, as Kas, Kbs, and all these other kinds of things we've seen so far. In this particular section, there is a handout I'd like you to look at if you get a chance. It's called the Solubility Guide. It's in the companion and it's on the website, but it talks more about solubilities and how you can convert a solubility to a KSP and KSP to solubility. Lots of cool kind of things in that handout, so I do recommend you check it out. Here are some representative KSPs that I just happened to find, and look at all of those KSP values. So first of all, it says 25 degrees. They are temperature dependent, and we'll talk about that later. But anyway, all of those KSPs are numbers less than 1. So what that tells you right away is all of these compounds, they will form a solid very readily. All right, there's barium sulfate. That was one of the ones in Chem 221 I wanted you to know. It almost always forms a solid. Calcium hydroxide, that'll be the purpose. We'll look at that in a future lab coming up, but that's very insoluble. Calcium carbonate, there's the silver chloride, silver bromides, etc., etc. All of these KSPs are going to be less than 1. There's a lot of cool things you can do with KSP, and we'll talk about those as we go through this area. But for right now, just realize none of these KSPs are numbers you have to know, okay? They're numbers that you can look up, use the all-powerful Google, whatever you need to do, and figure out what they are.
When solid lead chloride is added to water, a small number of ions are released into solution. Those ions can reattach to the solid, while other ions can dissolve. A state of dynamic equilibrium is reached, in which the concentrations of ions are constant and can be described by an equilibrium constant expression.
The KSP for lead 2 chloride is 1.9 times 10 to the minus 5, and we can figure out what the solubility of lead 2 chloride is from the KSP. What we can tell from the KSP is that because K is less than 1, PbCl2 really wants to form, but it doesn't explicitly tell us this solubility, like how many moles of lead 2 chloride will dissolve per liter before we start making any solid appear. And we'll talk about again how to go from KSP to a solubility and back and forth. So here's a question you might see. Which of the following correctly displays the equation used to describe the KSP for barium fluoride dissolving in water? Okay, so this is a question where first thing you must know is what exactly barium fluoride is, and that's a great question. Well, barium is a group 2A alkaline earth metal, so it has a positive 2 charge. Fluoride is a group 7A nonmetal with a negative 1 charge. So when barium and fluoride come together, it's going to be BAF2, okay? BAF2 is the formula for barium fluoride. So right away, this cannot be answer D. That's the incorrect formula for barium fluoride. Now, when you're writing a KSP expression, you always have the solid on the reactant side, and the ions that go into it are the products, all right? So if you look at the first one there, A, barium fluoride is right, but it's not going to go barium fluoride solid to barium fluoride aqueous. That doesn't sound right. The second one, B, looks a little closer, and remembering that fluorine is one of the 7 diatomics. Have no fear of ice clear brew. F is the fear of that one. So it's tempting maybe to think about it as F2, 2 minus. But the F2 part, the diatomic, only applies if it's neutral fluorine. And this is not neutral fluorine. These are the ions of fluorine. So if you're going to write fluorine as an ion, or the fluoride part, you want to write that as F minus. And you have 2 of these F minuses with barium. So in these 5 possible answers, answer C is the one you want. It's got the solid on the reactant side. It has the ions that make it up on the product side. Fluoride is individual F minuses, so there's going to be 2 of them. You're good to go. Answer E is close, but reactants and products are reversed. That would be like 1 over KSP, which might be interesting. But for a true KSP expression, solid on the reactant side, ions that go into it on the product side. Let's go back to PbI2 a little bit. PbI2 solid going to Pb2 plus 2I minus. That's the KSP expression here. So let's find the KSP value if the solubility is 0.00130 moles per liter. Now I want to step back for a second and just remind everybody, solubility is a threshold amount, and that's a moles per liter, and that says how many moles of PbI2 can dissolve per liter of water. If you're under that amount, you don't see a solid. But if you go even just a tiny bit above that amount, that's when you'll start to see the yellow PbI2 crash out of solution or form a precipitate. So what we're going to do in this problem is convert the solubility, how many moles of the solid dissolve per liter up until seeing a solid, we're going to turn that into a KSP, and it's not too bad. Solubility, again, refers to how many moles of a solid dissolve per liter. And when you go above that number, you'll see a solid form. If you're under that number, you won't see a solid form. They should be all able to dissolve in that amount of water. Solubility is literally the moles of PbI2 that can dissolve per liter of water. And notice how PbI2 and lead 2 plus 1-to-1 ratio. So if the solubility of PbI2 is that 0.00130 moles per liter, and you get 1 mole of lead 2 plus for every 1 mole PbI2, the solubility of the lead 2 plus is going to be the same as the solubility. It's 1.30 times 10 to the minus 3. So solubility and the amount of lead that's dissolved are the same number here, and that can be a little strange. The iodide is, of course, part of it too. Iodide will be twice the lead. Stoichiometry again, 2 I's for every 1 Pb2 plus. 2 iodides dissolve for every mole of PbI2 in the solubility. So iodide here is going to be 2.60 times 10 to the minus 3. Notice here again how stoichiometry of the balanced reaction is so important. 2 I minus per 1 lead, we multiply the lead by 2 to get the iodide, no problem. There's a couple ways you can go from here. We want to find the KSP, okay? And one way you could do it was you could just plug the lead value in, this number, and multiply it by the iodide squared. Remember, this is an equilibrium expression, products divided by reactants. No reactants, because our only reactant is a solid, but we do multiply or square the iodide, multiply it by a factor of 2 because of the stoichiometry of 2. So again, you could take 1.30 times 10 to the minus 3, the lead 2 plus, and multiply it by 2.60 times 10 to the minus 3 squared, and that would be fantastic. But notice this version as well. You could also take the iodide, and iodide was equal to 2 times the lead. So there's a reason why I'm doing this. I'll talk about in a little bit. So 2 times the lead, quantity squared, because we still have to deal with that thing. 2 squared is 4. Lead 2 plus to the second power is lead squared, but we're multiplying it by this lead 2 plus. 4 times the lead 2 plus to the third power would be one way to solve for this KSP. And I'll talk about why I'm doing it this way here in just a second. To figure out KSP, there's 2 ways you could do it. You could literally take the lead and multiply it by the iodide squared, and that's fantastic. But if you go through a little math, you'll also see that KSP equals 4 times the lead ion to the third power. And there's a use for that here. I'll show you in a little bit. Anyway, whichever way you do it, you can absolutely get the right value. Lead 2 plus, remember, was equal to the solubility. So you can rewrite 4 times lead 2 plus to the third power as 4 times the solubility to the third power. I'm going to do my problem this way. I'm going to take that solubility and cube it first and then multiply by 4, KSP 8.79 times 10 to the minus 9th. Now, again, you would have gotten the same value if you would have taken 0.00130, the lead, and multiplied it by 0.00260, the iodide squared. It doesn't matter which way you do it, but this 4 times the solubility to the third power equals KSP will be helpful to us here in a little bit. But this is one way that you can calculate then KSP from solubility. So in this problem, solubility was related to PbI2, and if you think about solubility as X, KSP equals 4 times x to the third power. The solubility to the third power times 4 equals KSP. And you're probably like, what are you doing, Russell? Have you been out smoking or something? And no, just say no, kids. There's a reason for it. A lot of times, a scientist will have KSP and they want solubility. Or, like in this problem, you'll have solubility and you want KSP. And you can actually go through stoichiometry and figure out the different pieces. But if you know the relationship between KSP and solubility X, it does make your life a little bit easier, which I know is kind of strange sounding. This page shows the different relationships between solubility X and KSP. Now, in the first one up here, there was 1 cation and 1 anion. So for things like sodium chloride, KSP would be sodium ions times chloride ions. And because solubility is how much of each of those are created, it would be like X times X or X squared. So if you had a KSP for NaCl and you wanted to find the solubility, you could take the square root of KSP and that would equal solubility. And that also works for things like strontium oxide, which are 1 cation to 1 anion. Potassium chlorate would be 1 K plus and 1 ClO3, 1 cation to 1 anion. All of those work really well. Now, the next two are very similar. If you have one cation and two anions, like PbI2, or if you have two cations and one anion, then KSP equals 4 times x to the third power. So in the last example we were looking at, I think it was lead to iodide, PbI2, if we had the solubility to the third power times 4, that's going to be a great way to find KSP. And again, that works for any time you have two cations and one anion, or one cation and two anions. Those three examples are going to be very common. However, you can figure these kind of things out for other systems too. If you have a 3-to-1 ratio of cations to anions, KSP equals 27x to the fourth. And if you have two cations and three anions, or three anions and two cations, KSP equals 108 times x to the fifth power. And believe it or not, I have used all of these at different times to calculate solubilities, KSPs, and stuff like that. And it's a little bit easier if you can do the solubility x to KSP conversion. Let's look at some examples. So let's say we wanted to find the solubility of copper 2 phosphate if KSP equals 1.4 times 10 to the minus 37th. So what we would have to do in a problem like this is first of all find that ratio of cations to anions. Well, copper 2 means copper 2 plus, and phosphate, a polyatomic ion, PO4 negative 3. So when they come together to make a neutral compound, you can use crossover or whatever you want, Cu3 PO42, that would be the formula for copper 2 phosphate. We have 3 cations and 2 anions. And if I'm correct here, KSP equals 105 times x to the fifth. Let's see if I was right. 108 times x to the fifth. Sorry about that. So because there are 3 cations, 3 copper 2 pluses, and 2 anions, 2 phosphates, this is a 5 total anion ratio, 3 cations, 2 anions. And the relationship, if you look back to that slide, between 3 to 2 and a KSP, it's 108 times x to the fifth equals KSP. So in this problem, we have the KSP and we want to find x, the solubility. So you can take the 1.4 times 10 to the minus 37th, first divide by 108, and that'll give you solubility to the fifth power. And then you need to take the fifth root, which is like raising it to the 1/5 power. In your calculator, this can get kind of messy, but it's actually pretty easy to plug and chug once you see it. Here's the KSP. We're dividing it first by 108. And to get rid of that x to the fifth, you raise it to the 1/5 power. Just like 2 squared is 4, and the square root of 4 is 2, and the square root is like 1/2. So x to the fifth, the opposite of that, if you will, would be 1/5. All right, that's where that comes from. Anyway, solubility, 1.7 times 10 to the minus 8th moles per liter. So copper 2 phosphate will not form a solid unless those ions are pretty small, like that number right there. In reality, the copper would be 3 times that number, and the phosphate would be 2 times that number. But don't even worry about that right now. This is a cool way to go from an equilibrium constant back to solubility, or from solubility to KSP. Here's another problem. What is the KSP for magnesium carbonate if the solubility is 2.6 times 10 to the minus 3? Now, magnesium is a positive 2 alkaline earth metal, carbonate a polyatomic ion, CO3 minus 2. This is a 1-to-1 ratio, 1 magnesium for every 1 carbonate. So this solubility is going to be related to KSP by KSP equals x squared, because we only have 1 cation and 1 anion. So solubility squared in this case is going to give you KSP. If you take that 2.6 times 10 to the minus 3 and square it, that's going to give you KSP 6.8 times 10 to the minus 6. Now, at this point, you might be thinking, Yeah, whatever. All right. And I totally understand. You also might be thinking, hey, why don't they just talk about solubility and forget the equilibrium constant? And that's a really good question. Equilibrium constants, KSPs, have a lot more uses than just converting back and forth to solubility. So one of the uses of KSP is to calculate the solubility, i.e., if you put the solid in water, how much of it will dissolve, or how much do you have to stay under in order for it to remain dissolved. So that's a cool use of KSP, but we're going to see there's other uses of KSP besides just solubility, so hang tight. The solubility of barium sulfate, 1.05 times 10 to the minus 5. What's the KSP? Well, barium sulfate, if you remember from before, it's a barium 2 plus and a sulfate negative 2. They come together 1 to 1, BaSO4. So BaSO4, 1 to 1, cation to anion, means the KSP here would equal barium 2 plus times sulfate, or if we're talking about solubility, KSP equals solubility squared, x times x. And we have there the solubility number, so take that number and square it or multiply it by itself. The answer, 1.10 times 10 to the minus 10. So again, a very small KSP for a very insoluble compound. Here's an example with that weird mercury 2 ion. This is Hg2Cl2, which is very insoluble. It's breaking down to the mercury 2 plus ion and 2 chlorides. Now KSP for this reaction, 1.1 times 10 to the minus 18th. And again, that's going to equal the product of the ions, nothing on the bottom because no solids or liquids. KSP equals mercury 2 plus times the chloride ion squared. Now, let's say that we had a solution of this mercury 2 plus hanging around, and it was 0.010 moles per liter. And mercury is not exactly the best metal to be having around, and if you're not using it, you should probably dispose of it properly. And one way to dispose of things properly is to make a solid. If you make a precipitate, then you can filter out the solid, and shipping solid waste is a lot easier and a lot safer, honestly, than shipping waste with a solution, like the 0.010 molar thing is. So let's say we're going to be good people here and we're going to try and precipitate out the mercury 2 plus ion as Hg2Cl2. Well, if the mercury 2 plus is 0.010 and we know that KSP, the 10 to the minus 18th number, equals the mercury times the chloride ion squared, I wonder what chloride ion concentration, moles per liter, is required to begin precipitation of this Hg2Cl2 salt. And that's a really, really good question. This problem, when you see it, is a pretty easy plug and chug. You put the right pieces in the right equation and out the answer will come. But at first it can be kind of weird to see. Questions like this also show the utility of KSP. So instead of just finding solubility, i.e. when solids will appear, now we have an unusual amount of mercury and we want to see how much chloride it's going to take to make the precipitate crash out of solution, become a solid. The question really is even better, though, than I said it. So really the question is, what's the maximum chloride that can be in solution with that 0.010 molar without forming the mercury 2 plus, i.e. what is the solubility when you have 0.010 molar Hg2 plus ions? And that's a really, really good question. And we can use that KSP, this thing up here, to plug it in. And honestly, it's pretty chill. This number goes right there. We've got KSP. We're going to solve for chloride ion. It's going to be squared, so we have to take the square root, etc., etc. So let's do that. KSP, 1.1 times 10 to the minus 18th, the number you can look up, equals mercury ion times chloride ion squared. Mercury ion was the 0.010. Now, KSP is the product of the maximum ion concentrations. When you go over these thresholds, that's when a solid begins to appear, and when you're under the thresholds, then you don't have a solid. So when we figure out what this number is, all right, we're going to get a number. And if you go just a little bit above that number, that's when you're going to see a solid form. It's when it exceeds the KSP, the maximum ion concentrations. And in this case, we're going to find that threshold for chloride and see when the solid will start to happen. going back to my plug and chug equation, the KSP 1.1 times 10 to the minus 18th equals 0.010 times chloride ion squared. So we want to solve for chloride. That's literally all we do. So chloride squared is going to equal KSP divided by the mercury, 0.010. To get rid of the squared, we'll take the square root of both sides. So KSP 1.1 times 10 to the minus 18th divided by 0.010, and square root of all of that, 1.0 times 10 to the minus 8th moles per liter. And this number is actually pretty helpful to chemists, because once you go past that amount of chloride, you're going to start seeing insoluble Hg2Cl2. If you go to 1.01 times 10 to the minus 8th moles per liter chloride, you're going to see a solid. However, if you're only at 0.9 times 10 to the minus 8th molar, a little less than that, no solid is going to form. So that's the utility of this kind of thing. It doesn't take a lot of chloride to make this stuff crash out, to make it precipitate. It's easy to have 10 to the minus 8th. Goodness, in the lab we'll use 0.1, 0.01, 0.001 maybe solutions. 10 to the minus 8th is very, very small. Let's say that we know that it's the 10 to the minus 8th moles per liter needed to make the precipitate crash out. Let's add a lot of chloride. Chloride is cheap. It's in sodium chloride. Even hydrochloric acid isn't too expensive. So let's really push the chloride up. If you push the chloride to 1 moles per liter, when the mercury was initially 0.010 moles per liter, well, by Le Chatelier's principle, if you add a lot of product here, chloride, it should make the reaction move to the left. So the mercury, which was 0.010, should be a lot less as we pump the chloride up to 1 mole per liter. And we can use this technique to calculate the new value of the mercury ion at this point. So KSP equals the mercury ion times the chloride squared. But in this example, we're solving for the new value of mercury. And mercury at this point will be KSP divided by the chloride squared, which is just 1 squared. So lo and behold, mercury 1.1 times 10 to the minus 18th moles per liter. And when you think about these numbers a little bit, we took a solution which was 0.010 moles per liter, and we dropped it. We kicked it way down. So now the mercury ion concentration, 1.1 times 10 to the minus 18th. And so if we were trying to get rid of the mercury, that's pretty good. That's a reduction of concentration by 10 to the 16th, 10 to the minus 18th versus 10 to the minus 2 in the initial thing. That's pretty powerful. That's pretty cool. But it's also worth pointing out that we have not lowered the mercury to 0 moles per liter. All right? It's a very, very small number. 10 to the minus 18th is very, very small, but it's not 0. And you as a scientist and as a person and as a member of society need to figure out, is a 10 to the minus 18th moles per liter mercury concentration safe? Is that a good number to drop it to? Most people, I think, would say yes, that's pretty safe, but some people maybe don't. And this is something you need to think about as a person. I'm not going to tell you what's right or wrong. I do want to point out, though, that you can lower these concentrations a lot, orders of magnitude less than they were. But you as a person and as a member of society and all that kind of jazz, you need to think about if that's a truly safe level or if you need to add more in order to make the concentration go even lower. And finally, I don't think it's really possible in most situations to get that value down to 0, to literally have 0 moles per liter mercury to, unless you have something like sodium and water, which is very, very product favorite. It's very difficult to get these down. You can get them very, very low, but they won't go to 0. And that's kind of an interesting thing. That's an advantage and a disadvantage, arguably, of equilibrium. Here's a question. What concentration of carbonate is required to begin the precipitation of insoluble strontium carbonate from a solution which has 0.050 molar strontium 2 plus? And there's the KSB for strontium carbonate, 5.6 times 10 to the minus 10. Okay, most of the time, all right, you're going to solve for one of the missing pieces in the KSP expression. And for this problem, you would write SrCO3 solid in equilibrium with the ions strontium 2 plus aqueous and carbonate. aqueous. And again, I can't draw on this thing worth anything, so I apologize. But KSP would equal the strontium times the carbonate. And you can see here that you have a concentration of the strontium and you have a KSP for this thing. So the only thing you don't have then is the carbonate, the concentration of the carbonate. That's what you want to solve for here. So you can take KSP and divide it by 0.050, and whatever that is, that's going to be the answer. So when you do that, it comes out to be 1.1 times 10 to the minus 8th. That's the level of carbonate required to precipitate strontium carbonate from a solution. And again, it's pretty small. Strontium carbonate really wants to form. That's a very small K. Good to go. When we talked about buffers in the last section, we used buffers and we talked about the common ion effect, how you can use the addition of the conjugate to understand changes to pH and stuff like that. Well, we can use the common ion effect here with solubility as well. And this is a really kind of interesting phenomenon. If you look down in the lower left-hand side, the kind of test tube, really a centrifuge tube on the left there, it has some silver acetate, which is made up of Ag plus and acetate CH3CO2 minus ions. And the solid is right here, but because this is a solubility, you also have the ions. So you can see how there's acetates and silvers kind of floating around on the top there. All right, no big deal. Well, let's say that we decide to add extra silver nitrate, okay? Now, silver nitrate is not really part of the Ag acetate kind of equilibrium, all right, per se. But the silver in silver nitrate is a common ion to the silver acetate equilibrium, okay? So as you add more silver, you can notice there how on the first picture on the left, you had 1, 2, 3 acetates in solution kind of running around. And then right here, it shows adding the additional silver nitrate. And then finally, on the right-hand side, notice, and this is not an accident, there's only 1 acetate left over. So adding silver to a silver nitrate or silver acetate equilibrium forced the reaction to move towards the solid side, and more silver acetate precipitated out. So at the end, you end up, first of all, with less acetate. There were 3 ions of acetate, now there's only 1, okay? The silver ions, roughly about the same, maybe a little bit larger, but you also end up with a new counter ion, in this case, nitrate. Now, why this is important is that if you have some kind of nasty ion in solution that you need to get out, precipitating it out with some kind of common ion is a very cool thing to do, all right? It gets the bad ion out of solution and you end up with more solid. And remember, solids you can filter out pretty easily, and they're easier to ship away for waste containers and stuff. But in the process, you do end up adding another kind of ion. Now, probably nitrate is more benign than acetate, all right? Nitrate is pH neutral, as we saw in the last section, while acetate actually has a slight basic function. So maybe it's good to exchange, if you will, nitrate ions for acetate ions. So the acetate goes into the solid form and you can precipitate that out. But you can't get something for nothing. And that's another thing I want to point out. You may have lost acetate ions here, but now you have a bunch of nitrates running around, and maybe that's good, maybe it's bad. It's something you just have to realize as you go through this stuff.
In the test tube is a solution containing lead ions. To this we add a solution containing chloride ions, and lead chloride precipitates. Solid lead chloride is in equilibrium with lead ions and chloride ions in solution. At this point, we add more chloride ions in the form of a sodium chloride solution, which disturbs the equilibrium. More lead chloride precipitates, which removes still more lead ions from solution.
So in this video, which I like a lot, by the way, we're thinking about getting rid of lead ions. And lead in the 70s especially was seen as a really bad metal. Apparently it's a little bit sweet when you eat it. People made paint out of it. Little kids would eat the paint because it was sweet and tasty. Long story short, and the paint's no longer supposed to anyway have lead. But anyway, neither here nor there. Let's say we have a lead 2 plus solution and we're trying to get the lead out of solution. Okay, well, what we're doing is we're adding essentially sodium chloride solutions to the lead. Okay, now as you add a chloride source, chloride from sodium chloride is an ion common to this equilibrium. Chloride is a product, so adding chloride shifts the reaction to the reactant side, the side with the solid. And in the process, you can see the lead concentration goes from a higher value to a less high value. The lead is being pushed into the PbCl2. And that's what the top graph here is. That's showing you the PbCl2 that's precipitating. And after the first chloride addition, you definitely have PbCl2 precipitating out. Your lead ion is less, but notice now we do have chloride. And even though it doesn't state it, we also have sodium ions, which is probably okay, but still. Now, if you really want to get that lead out, heck yeah, add another NaCl solution. And that's what then this last part is right here. Well, additional NaCl adds more chloride. And like we saw earlier, more chloride makes the reaction go to the reactant side. Lead ion concentration is as low as it is anywhere. In the process, though, now we do have more chloride, all right? Because again, this is equilibrium, and the chloride is pushing the lead out, but of course then you end up with more chloride. The PbCl2 is easy to get out. We'll precipitate that, filter it, whatever, get rid of it. There would be sodium ions. So common ion effect can be really useful for getting out specific ions. If you do it right, like in this case, you can really get out the bad stuff, all right? On the other hand, in the process then, you end up adding different kinds of ions. In this case, like chlorides or sodiums and stuff like that. So it isn't a perfect system, but it can be really useful when you have an ion you really want to get out of solution. Let's calculate the solubility of barium sulfate in pure water and also when there's some barium present, okay? Now, barium sulfate in pure water, no big deal. There's the KSP for barium sulfate, 1.1 times 10 to the minus 10th. So this will be a problem like we looked at earlier when we converted KSP into solubility. You can see that one barium ion and one sulfate ion come from every barium sulfate. So that's like an x times x or x squared. So this is an x squared equals KSP. We can solve for the solubility that way. The second part, though, will be a little bit more interesting because we have barium already present. Barium is a common ion to the barium sulfate KSP expression. And if you think about having a barium sulfate KSP expression and you start adding in some barium, well, barium ion is a product. It's going to shift the reaction to the left side. We'll see how this affects solubility here in a little bit. But let's get rid of the first part first. The solubility, like I said, is oftentimes represented as X. You can represent it as anything you want to. And that solubility literally is the moles of barium sulfate that dissolve per liter in order to make a solid. But because it's 1-to-1 with barium ions and sulfate ions, barium ions equals sulfate ions equals solubility. And again, to find solubility, take the square root of that KSP, square root of 1.1 times 10 to the minus 10th, X value 1.0 times 10 to the minus 5 moles per liter. So we would say that the solubility of barium sulfate in pure water, if we put literally barium sulfate right in pure water, solubility 1.0 times 10 to the minus 5. So as long as we put in less than 1.0 times 10 to the minus 5 moles of barium sulfate per liter, no solid. But that's a pretty small number. It'll probably be easy to get over 1.0 times 10 to the minus 5 moles per liter. Then we'll start seeing a solid. And it's easy to get bigger than 10 to the minus 5 moles per liter. So yeah, we'll see barium sulfate pretty readily. This is a 1-to-1 ratio of cation to anion, 1 barium, 1 sulfate. So X times X, X squared equals KSP, etc., etc. We'll see a lot of X squared equals KSP for 1-to-1s. We'll also see some 4X cubed equals KSP expressions when you have 2 anions and 1 cation, or 2 cations, 1 anion. Now, for the second part, the solubility in the pure water, 1.0 times 10 to the minus 5 moles per liter. In the second part, though, we've already got some barium. You can also think about this problem as you have the pure water and you're adding barium ions to it. Well, if you think about it that way, you're adding a product. You're adding barium ions. We would predict that adding barium is going to move the reaction to the left-hand side, to the side with the precipitate. That means that you're going to have a harder time getting things to go into solution, all right? So down the bottom, which way will the common ion shift the equilibrium, i.e. you're adding barium, a product, it's going to shift to the opposite direction. We would expect a shift to the left, to the reactant side. Now, if you shift to the left, that means that less barium sulfate will be dissolving into barium and sulfate ions. So we would predict that the solubility of the barium sulfate will be less in the barium solution than it is in pure water. You can think about it like if there's already barium there, the barium is less likely to break away from barium sulfate. All right, there's already things there. But we can do this. We can actually figure this out using some pretty simple math. We can make an ice table, all right? And for this one, barium and sulfate are the only things in the ice table. We don't put solids or liquids. Barium sulfate, again, is a solid. Now, we initially have some barium, 0.010, and we don't have any sulfate ions. Now, to make it clear that this is not a regular solubility, which I've been using X, I'm going to use a Y here for my variable, but you can use any variable you want. The important thing is that sulfate can't be 0, it will increase. So barium will be 0.010 plus this Y, and sulfate will just be equal to Y. You can take those equilibrium concentrations and set them equal to the KSP, the 1.1 times 10 to the minus 10th. So 0.010 plus Y will be barium, Y will be sulfate, and all of that equals KSP 1.1 times 10 to the minus 10th. This is a quadratic formula as written. You'd have y squared plus 0.010y minus KSP equals 0, and you could go from there and figure that out. However, in pure water, the little y value was 1.0 times 10 to the minus 5, a small number, especially when compared to 0.010. And in the barium solution, by Le Chatelier's principle, we expect the value, the 1.0 times 10 to the minus 5, to be even smaller. Barium ions are shifting the equilibrium to the reactant side, so y should be an even smaller value. So for all of those reasons, it's absolutely okay to ignore that plus y. And that makes, again, your math a lot easier. KSP equals 0.010 times y. And if you solve for y, that just is 1.1 times 10 to the minus 10 divided by 0.010, 1.1 times 10 to the minus 8 moles per liter. Now, this number is the solubility. It's how much barium sulfate is breaking down to ions, but in the presence of the barium. And that's a number smaller than the 1.0 times 10 to the minus 5 number that you saw for pure water. The barium ions are common to the KSP equilibria. The barium is making the solubility decrease, all right? The solubility value there is less than the 1.0 times 10 to the minus 5. Barium made the solubility go down. So if you don't want your barium sulfate to break down, you can add a little barium to it. That'll keep the solubility much, much smaller. So, to summarize, the solubility of barium sulfate in pure water, 1.0 times 10 to the minus 5. In the presence of the barium, though, the solubility went down 1.1 times 10 to the minus 8th. And again, Le Chatelier's principle came through for us once again. We added barium ions, which was a product. If you add something, it's going to move to the opposite side, move to the reactant side. That means that we should have less barium and sulfate dissolved in the presence of the excess barium. And that's what we're seeing here mathematically. It went from a 10 to the minus 5 molarity solubility down to 10 to the minus 8. So that's a pretty good jump down there. So again, Le Chatelier's principle is followed. Woohoo! Good for Le Chatelier. Getting too excited.
In the test tube is an aqueous solution containing ions of silver, lead, and copper. When we add chloride ions, a precipitation occurs, producing solid silver chloride and solid lead chloride. The copper ions remain in solution, indicated by the blue color of the liquid, which is decanted. We add distilled water to the test tube and heat it. Lead chloride is soluble in hot water and returns to solution. We again decant the solution in the test tube, leaving solid silver chloride. To demonstrate that the decanted solution contains lead ions, we can add chromate ions, which cause the precipitation of lead chromate. The characteristic yellow color of the precipitate confirms the presence of lead. We have separated the three ions in the original solution from each other.
This video is pretty cool. You start with a test tube that contains copper 2 plus, silver plus, and lead 2 plus ions. And the goal here is to separate out all three of the ions, one from each other. So you'll have just a test tube of copper, a test tube of silver, a test tube of lead. Now, I say to separate out, we're going to separate out most of it, all right? Like we talked about earlier with the mercury example, we probably won't get all of it out, but we're going to get a lot of it out. And using some simple tests, we can kind of make sure that at least most of the ions are separated out from each other. So that one caveat aside, this is pretty cool. First thing they did is they added a source of chloride. All right, you could add HCl, you could add NaCl, but the reason they did that is AgCl and PbCl2 are very insoluble. So they quickly made like a white solid and they decanted. Decant means to pour the liquid off carefully and keep the solid in the test tube as much as possible, okay? And so the stuff they decanted, the liquid form, that had the copper ions. And copper 2 plus has a very powerful blue color, which you can see on the left test tube right there. So that's how they separated out the copper. Copper 2 chloride is not very insoluble. It's very water soluble, as a matter of fact. Most chlorides are aqueous unless they're with silver, lead, or that mercury thing. So that got the copper out. Now the next thing is they needed to separate out the silver chloride from the lead 2 chloride. And this is something we'll talk about later, but lead 2 chloride actually dissolves pretty well at higher temperatures, while silver chloride does not. So they took the test tube with the AgCl and the PbCl2 and they placed it in boiling water. And the PbCl2 went into the liquid phase. It actually dissolved, all right, while the AgCl did not. So again, they decanted out the liquid from the solid. The liquid should have PbCl2 and the solid should have AgCl. But to make sure that the liquid phase had PbCl2, they added chromate. And chromate with lead makes a really bright yellow color. It's a pretty cool color, actually. So that proved, if you will then, that the lead had been transferred to the new test tube. The only thing different I would have done here was I would have added chromate to the silver test tube as well. Silver and chromate makes kind of a red color, so you could have confirmed and stuff that that was there. But either way, no big deal. This is how chemists separate out ions from one another. It's a pretty good value, all right? Most of the silver is separated from most of the lead, from most of the copper. Probably not all, all right? If you really were worried about any of those, you'd have to do something a little greater. But at least to the first order, this is a pretty cool way to separate out one from the other based on differences in KSP. key. Now, the difference in temperature, solubility, is something we'll talk about more in the next chapter. But for right now, just realize that some compounds, it's easier to dissolve them at warmer temperatures than other ones, and that's something we'll see later. So this is a kind of question you might see, all right? We have a solution, and it has 0.020 molar silver ions and 0.020 molar lead 2 plus ions. And we want to separate the two of them out. Now, chromate is a great thing to add, great polyatomic ion to add here, because both red Ag2CrO4 and yellow PbCrO4 are insoluble compounds, but they're not soluble to the same level. And here are the KSPs for the compounds that form, and you can see that there's a little difference between them. They're not the same number, all right? So in a question like this, it might be nice to know if we added chromate in really, really small amounts, which would we see first? Would we see the yellow PbCrO4 or would we see the red Ag2CrO4? And we can absolutely solve for this. Now, what we're going to do is we're going to have two kind of simultaneous equations going on at the same time. One will be the KSP for Ag2CrO4. So this 9.0 times 10 to the minus 12 number, that's going to equal the silver ion concentration squared, and this is the silver ion, and we're going to solve for chromate, okay? In the other set of equations, we're going to use the other KSP, the 1.8 times 10 to the minus 14th. That equals the lead 2 plus, which we're also given, 0.020, and we're going to solve for chromate there. Once we have the two values of chromate, one of the numbers will be smaller than the other one. And the smaller value, that's going to be the indication as to which one precipitates out first. Because if we add really, really small amounts and we add just that smaller number, that's going to make a solid. The one that needs more chromate is going to take extra chromate to make a solid, and that one would precipitate last. So again, the math is not too hard here, but thinking it through can be a little bit weird. Remember that the substance whose KSP, the values there, is first exceeded will precipitate first. So we really kind of want to solve for the chromate here. We want to see which one is going to take the least amount of chromate. Smaller amount of chromate will be the one that precipitates first. We're going to calculate again the chromate required by each ion. So let's do the silver chromate first, all right? So KSP for silver chromate equals silver plus squared times chromate, and we want to solve for chromate. So chromate will equal the KSP number, this thing, divided by the silver ion squared, because it's squared because of the 2 right there. The chromate required, 2.3 times 10 to the minus 8th moles per liter. And that's a very, very small amount of chromate. It's not going to take much chromate to make the red Ag2CrO4 precipitate out. But we should check the lead 2 chromate as well, of course. So let's do the same kind of calculation, but for lead 2 chromate. Lead chromate, KSP equals Pb2 plus times chromate, or chromate equals KSP, the number given, divided by the lead, that number, and lo and behold, 9.0 times 10 to the minus 13th. Well, if you compare these two numbers together, the chromates required, you can see it actually takes quite a bit less chromate to make PbCrO4 precipitate than it does the silver. If we're adding very, very small amounts of chromate, if we added 9.0 times 10 to the minus 13th moles per liter chromate, that will make the yellow PbCrO4 precipitate out. On the other hand, we have to go many orders of magnitude higher, i.e. 10 to the minus 13th to 10 to the minus 8th. We have to raise that chromate several orders of magnitude to make the red Ag2CrO4 precipitate out. So PbCrO4 should be the first one to make a solid. So this question, we have 0.1 molar potassium sulfite and 0.30 molar sodium sulfate. Now, sulfite is SO3 and sulfate is SO4. And we're slowly adding in calcium nitrate. And the question is, which precipitates first, calcium sulfite or calcium sulfate? Okay. There's an unofficial way and an official way to do it. Let's talk about the unofficial way first, all right? Calcium sulfite and calcium sulfate are both 1 calcium to 1 polyatomic ion, 1 to 1, all right? And the concentrations of the sulfite and sulfate, 0.10 and 0.30, are pretty close to each other. Most of the time in these cases then, smaller KSP will tell you which one precipitates first. So because the calcium sulfite is 1.3 times 10 to the minus 8, and that's a lot smaller than the 10 to the minus 5, I'm going to predict that calcium sulfite is going to precipitate first. That's the unofficial way. Smaller KSP often means precipitate first, while larger KSP would mean precipitate last. Now, the official way to do this would be to set 1.3 times 10 to the minus 8 calcium sulfate equals the calcium, our unknown, times sulfite, and sulfite is 0.10, and you'd solve for calcium. You do the same thing for calcium sulfate, 2.4 times 10 to the minus 5 equals the calcium, the unknown, times 0.30, the sulfate, and you'd solve for calcium. Either way you do it, you're going to see calcium sulfite is the smaller one. I didn't even do the math on this one because, again, sulfite and sulfate are both within in the same order of magnitude. And the difference in KSP was quite a bit, about 3 orders of magnitude. So sulfite and sulfate really aren't going to make a difference. Calcium sulfite is going to precipitate out first. And if you don't believe me, absolutely go through the math. You would take 1.3 times 10 to the minus 8 and you divide by the sulfite, 0.10. You do the same thing for calcium sulfate, but you take that KSP and divide by 0.30. And you should see that this one is smaller than the other one. Again, that 10 to the minus 8th versus 10 to the minus 5 makes a big deal. Here's a question that's similar to the last one. We have a solution now, 0.020 molar silver ions and 0.020 molar lead 2 plus. We saw that PbCrO4 in the earlier example precipitates first. There's the KSPs. This is another kind of twist you can put on these kind of problems. If you really want to separate out the silver from the lead, how much lead remains in solution when the silver plus just begins to precipitate? This is another kind of common question you might see. You really want to get the lead out of the silver. And as you start adding chromate up to the point where the silver chromate crashes out, then you can actually start pulling the lead out. You can use decanting or you can filter it, stuff like that. So remembering that lead started at 0.020, let's see how much is left when the silver ion begins to precipitate. From the last example, the chromate required to make the Ag2CrO4 2.3 times 10 to the minus 8. So what we're going to do is we're going to solve for lead at this point. We're going to go back to the KSP for the PbCrO4, but we're going to put this number in for the chromate, and we're just going to solve for the lead. Mathematically, it's not hard, but sometimes thinking about these things can get a little weird. So if you do that, the KSP was 1.8 times 10 to the minus 14th. We're going to divide it by the chromate needed to make the Ag2CrO4 precipitate, 2.3 times 10 to the minus 8. And lo and behold, 7.8 times 10 to the minus 7th moles per liter. So what that means, if we add 2.29 times 10 to the minus 8th moles per liter chromate, our lead ion, which started at 0.020 moles per liter, went down to a number much less than 10 to the minus 6, all right? It's like 10 times 10 to the minus 7th would be 1 times 10 to the minus 6. So a pretty small amount. And in the chemistry world, that would be separating. Obviously, the concentrations didn't go to 0. That's the joy of equilibrium, but at least it's a lot less than it was. We're going to look here real fast at complex ions and formation constants once again. We looked at these back with the Lewis acids and Lewis bases, but they can be really helpful, especially when combined with a KSP expression. So we've already seen, for example, in lab and in lecture, some complex ions. It's usually a transition metal with different ions around it, different Lewis bases. The transition metal is the Lewis acid, and the things with lone pairs on them are great Lewis bases. Formation formation constant, again, is just taking the individual pieces to make the complex ion. So for the AgCN2 thing, you would have 1 silver and 2 cyanides as your reactants, and the complex ion would be the product. So notice this is kind of the opposite of KSP. KSP had the solid as a reactant, and the products were the ions. And here it's like the ions are the reactants and the complex ions are the products. But anyway, the KF for this one, 5.6 times 10 to the 18th, very large, very product favored. They form really easy. They freak chemists out sometimes when they don't understand what's all going on. This is the joy of the formation constant. Formation constants can be looked up in tables just like KSPs or KAs or anything like that. And again, notice that all of these numbers here are pretty big numbers. That means all of these complex ions are ready to form, ready to go. In these kind of KF expressions, remember the ions are the reactants and the complex ion is the product. They're almost always written as net ionic reactions, similar to what the KSPs were too, just FYI about that. So remember about complex ions, you're usually going to use a net ionic reaction. You don't include the spectator ions like we talked about in Chem 221. We talked about how you can use ammonia to help dissolve silver chloride, and this is just another example showing this process. Silver chloride is very insoluble, but if you want the silver chloride to be dissolved, i.e. to get off your glassware, adding ammonia will actually make the silver ion complex with it, and the complex ion then will pull the silver chloride away. Here's the KSP expression for silver chloride solid going to silver ions and chloride ions. Let's combine that now with a KF expression. And remember, KF, the ions that go into it are the reactants and the complex ion is the product. Well, if you combine these two reactions together, you can actually calculate the net K for this kind of reaction. Notice how silver ion will cancel on both sides. You can see what happens. In this case, the silver ion cancels. K net would be KSP times KF. KSP and KF are both numbers that are fairly easy to solve. And again, you will see your silver chloride dissolve.
When solutions of silver nitrate and sodium chloride are mixed, insoluble silver chloride precipitates from solution. When we add ammonia to the mixture, however, the precipitate redissolves. When ammonia is added to a mixture of solid and aqueous silver chloride, the ammonia serves as a Lewis base. The complex ion formed consists of 2 ammonia molecules bound to each silver ion. Formation of the complex lowers the concentration of silver in solution, which changes the solubility equilibrium.
This used to really freak chemists out, all right, because like you're making silver chloride and you're like, oh, no problem, but oh, you accidentally add the wrong thing, and sometimes these complex ions start kicking in. So the main point of bringing this up is just to remind you that KSP's solid reactant and the ions that make up the solid are the products, but KF's for formation constants for complex ions, the ions that go into it are the reactants, and the complex ion is the product. It's kind of the opposite. So just remember that in the back of your mind. Okay, that's the end of chapter 15. I really appreciate you spending your time with me. To go further into this kind of material, I do recommend looking at this study guide for this chapter. It's a bulleted list of the highlights from this section. You can also look at the concept guide, worked examples of how to do some of these problems with KSPs and all that kind of jazz. There's several types of equilibrium constants. You can see them all in the types of equilibrium constants handout. It'll remind you what KF is and KSP and all that kind of stuff. The solubility guide, kind of cool. It does list different examples on how you can make solubility work for you, how to go from solubility to KSP and back and forth. Also, following these notes in the online version, you'll see a list of the important equations from this section, and I do have some end of chapter problems where there's the questions and the next slide follows the answers. I recommend you try and get them and stuff to make sure you've got this stuff going on. If you get stuck on this material at any time, don't be afraid to reach out to me and or the Learning Success Center / Avid Center located above the library or online. All of us are happy to help you, and we want you to get this. This is all stuff you can do. All right. Thank you for spending your time with me today. I really appreciate it. I wish you the best on this material, and have a wonderful day.